Transport phenomena refers to the study of how mass, energy, and momentum move through different mediums. It plays a crucial role in understanding various physical and biological processes. It has three key aspects: diffusion, osmosis, and viscous flow. Let's start with diffusion. Diffusion is the natural movement of particles from an area of higher concentration to an area of lower concentration due to random molecular motion. Movement will continue until a state of equal concentration occurs.
Gather all materials. Pour the same amount of warm water into the warm water glass. Pour an equal amount of hot water into the hot water glass. Hold the food coloring dropper just above the surface of the hot water. Add 1 drop of food coloring into the center of the hot water glass without stirring. Start the stopwatch immediately and observe the diffusion process. Repeat the same process. Watch how the food colorings record how long it takes for the color to flow. Take note of the patterns.
Food colorings spread faster in hot water compared to warm water. Diffusion happens quicker in hot water because the molecules move faster at higher temperatures. Heat increases the kinetic energy of water molecules, causing them to collide more frequently and spread the food coloring more rapidly. In contrast, in warm water, the molecules move more slowly, resulting in a slower diffusion process. This demonstrates that temperature directly affects the rate of diffusion.
Osmosis is the process by which water or other solvents move through a semi-permeable membrane into a more concentrated solution. The goal is to equalize the concentration of solute on both sides of the membrane.
Gather all materials. Label one glass as pure water and the other as salt water. In the saltwater glass, dissolve 3 to 4 tablespoons of salt in the water and stir well. Take 2 equal-sized potato strips. Place 1 strip into the pure water glass. Place the other strip into the saltwater glass. Start the stopwatch and let them sit for at least 30 minutes or longer for better results. After 30 minutes, take out both potato strips. Gently touch and bend each strip. Changes in texture, flexibility, and size. Measure any differences if needed.
We noticed that the potato in pure water became stiff, while the one in salt water became limp. Osmosis is the movement of water across a selectively permeable membrane from an area of low solute concentration to high solute concentration. In pure water, the potato cells absorb water, making them firm due to the higher water concentration outside the cells. In salt water, the higher salt concentration outside the potato causes water to leave the cells, making the potato limp as it lost water. This demonstrates how osmosis regulates water balance in plant cells.
Viscous flows occur when the effects of fluid viscosity are balanced by those arising from fluid inertia, body forces, and pressure gradients. In such flows, scaling analyses do not allow a priori neglect of any terms in the equations of fluid motion.
Gather all materials. Label one setup as water and the other as oil. For an equal volume, for example, 100 milliliters of water into the funnel connected to the first pipe. Start the stopwatch as soon as the water enters the pipe. Stop the timer when all the water reaches the measuring cup and record the time. Repeat the same process with the oil in the second pipe. Compare the time taken for each liquid to flow through the pipe. Observe how the water flows faster, while the oil moves more slowly due to its higher viscosity.
In conclusion, water flowed faster than honey through the pipe. This is because water has a lower viscosity, meaning it offers less resistance to flow compared to honey. Viscosity is a measure of a fluid's resistance to flow. Fluids with lower viscosity, like water, flow more easily because their molecules move freely with less internal friction. In contrast, thicker fluids like honey have higher viscosity, meaning their molecules experience more resistance and move slower. This principle is important in real-world applications, such as lubrication, transportation of liquids, and industrial fluid dynamics.